So so we will see now why is this the answer is still no in this case to our conformal embedding problem. So let's recall the what we are using here. So we are calling M this set is the matrix of negative curvature on sigma. B tilde of sigma, I will call it the set of matrix in negatively curved matrix that admits an isometric embedding in T mod gamma, so that they have an isometric embedding. And B of sigma, its projection into the Teichmüller space. Okay, so the idea is to prove that B of sigma is not the whole Teichmüller space. Okay. Okay, so we will prove something more than that. We prove that any metric in that admits an isometric embedding in T mod gamma is quasi-isometric, or it's B-Lipschitz to the hyperbolic metric H gamma, and the constant C here, the constant is it does not depend on the metric G. It depends only on gamma. Okay, and this will allow us to say that the set, when we see all the conformal structures in the Teichmüller space, this set B sigma will be relatively compact, and thus we will not get everything. Okay, so I recall that the distance between any two metrics, as we said before, it will be less or equal than 1/2 log k, where k is as follows. And since the metric is B-Lipschitz to H gamma with respect to with constant that does not depend on the metric, then all the metrics, their distance from H gamma will be, if we compute this k, it will be always less than c squared. Okay, uh, it will be always less than c because we are not taking that. Okay, so this means that the distance of the Teichmüller distance between the conformal between any metric between any conformal class in B sigma and the conformal class of H gamma is less than constant log C. I think there is 1/2 missing here, but okay. So this means that the set B sigma, it is included, it lies inside the ball of center H H gamma and of radius at most log C. Okay. So it is relatively compact, and hence it is not the whole Teichmüller space. So we cannot find all conformal embeddings. Okay, so how are we going to prove the theorem? The fact that all the negatively curved metrics embeddable that are embeddable are quasi-isometric to the hyperbolic one. So it worth nothing to lift everything to the universal cover. So let's take an embeddable metric. So we lift it into a metric on the universal cover of sigma. Okay, and here gamma, I mean by gamma the pi one of sigma. They are isomorphic. And since G is embeddable, admits an isometric embedding in T mod gamma, then G tilde, sigma tilde with the metric G tilde admits an isometric embedding in the cone, and this embedding will be equivariant, of course. If we act here on sigma tilde by the pi 1 and act here by gamma, then we have an equivariance. We have this condition. Okay. So the idea is to prove that the metric G tilde is quasi-isometric to the metric to the hyperbolic metric, and the constant, we need to prove that the constant is not it does not depend on the metric G, because this is any metric. Since we are on a compact surface, any two metric are quasi-isometric, but we need the constant to be independent. Okay, so just a remark is that so the metric G, we have this isometric embedding F tilde, okay, in the Minkowski space. And the metric G tilde, since it comes from a metric on a compact surface, the metric G tilde on sigma tilde is complete, okay? And we can prove that since this metric is complete, any space-like embedding is an entire graph. Is of the so the image is of the form is a graph of some function, uh, one Lipschitz function, and if we compute the curvature now, the curvature will have this form, and it is easy to see that if the curvature is negative, which is the case here, then U is strictly convex. Okay, because we see here that this is the determinant of the Hessian of U. Okay, so our embedding is just a graph of some function, and since the metric is negative, then it is the graph of a convex function. Okay, and this is a very striking fact that we will use so many times. Okay, so since we want to compare the metrics, the hyperbolic metric and the metric G tilde, we need this lemma, which says that the image, this is, as we said, it is graph over over R2, as I said before, but it is also graph over the hyperboloid H2. Like when we see, as I said, the cone is H2 times R. So we want to prove that F tilde of sigma tilde is just the graph of some function over H2 in this product. Okay. And this is equivalent to saying that the embedding of sigma in T mod gamma is a graph over S, over the hyperbolic surface. Okay. So this is equivalent to this. So as I said, the idea is the same. This is a space-like embedding. The kernel of the projection on the first factor on S is timelike. So the plane, so the restriction, when we compose with the projection, this will be a local diffeomorphism. And this will be by compactness and connectedness, this will be a covering map. And since we are in higher genus, this will be a diffeomorphism. And this implies that our embedding is a graph over S, and by equivariance, it will be a graph over H2. Okay. So I recall that this is what we want. We want to find C that depends on gamma such that we have this inequality. And the key idea is that this embedding, since they are a graph of convex function over R2, okay, over the XY plane, we will prove that it will be bounded by two levels. And these two levels, if we up to some scaling by constant factor, these two levels do not depend on the metric. This will give us what we want. Okay. So if we assume always that our graph is above is tangent and in the future of the hyperboloid one, the hyperbolic part, then there exists a level, okay, H2R, where any embedding is between these two levels. Any embedding of a negatively curved metric will be between these two levels. Okay, so this is the first idea. So as I said, so we have an embedding. It is the embedding of a convex function. Okay, up to scaling it, we can always assume that it is, as I said, it is tangent to some to the hyperbolic level H2 at some point P. Okay, but remember, it is the graph of a convex function. Okay, so by equivariance, it will be tangent at the orbit of P by gamma. Okay, since everything is equivariant. Okay, and now what we are going to do is that we are going to take the closed convex hull of the orbit gamma P. Okay, so So, so let me say this. So we have the hyperboloid. Okay, we have our point P. It has its orbit is right here. Okay, and now we are going to take the convex hull of this of the orbit, the convex hull in the usual sense. Okay, and our surface, our embedding f tilde, as we said, it is tangent to H2 at this point. Okay, so it is somewhere here. And since it is the graph of a convex function, and by definition, and it contains the orbit gamma p, then its hypergraph, it must contain this closed convex hull HP, because by definition this is the smallest convex set that contains the orbit gamma p. Okay, so the graph of f tilde, it will be between the hyperbolic level and this set HP, the boundary of this convex hull. Okay, so since our graph is always bounded by HP, the question is reduced just to saying that so this is what I said. The question will be reduced to prove that the boundary of HP is always bounded by some level. Okay, so the boundary, not the whole, because so we will find some level that does not depend on the point P, and does not depend on, so it does not depend on the point P, and such that this red curve will be always under the green one. So this is the level H2 alpha that we are looking for. Okay. So any embedding will be bounded by the level H2 and the level H alpha. Okay, and this will be the case because we will take the group, we took it to be cocompact. So first of all, we will prove that the boundary of the convex hull is always bounded by some level, and since the boundary this boundary depends on the point P, uh, 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 it does not depend on P, it depends only on the orbit of P because it is the same. So it depends only on P in some fundamental domain, and since gamma is compact, we can find a level that verify this. Okay, so this will give us the upper bound. Why? As I said, the f tilde is a graph of some function over the hyperboloid, and we just proved that any such function we can rescale it by some constant function, so that its image will be between 1 and alpha, and this means that the induced metric, which is actually the metric G tilde, is always less than alpha squared h. So it is always bounded by this. And alpha, as we said before, it does not depend on the metric G tilde. Okay. So this is for the upper bound, and for the lower bound we will use the convexity again. So as I said, it is a graph of some function f over h2, and we want to find c prime such that we have this inequality. So I just want to say that this is equivalent to saying that if we have if we are here in we have the isotropic cone. Okay, this is equivalent to saying that there exists a bigger cone. Okay, such that the tangent space of f tilde of sigma tilde will be always outside this cone. Okay, so it will not the tangent plane of f tilde of the image, it will be always far away from the isotropic cone. It will be uniformly far from the isotropic cone. With this in mind, this is what we are going to prove. So remember that, as we said, the image is a graph of a convex function over R2, okay? And by convexity, the hypergraph, if you take the convex function, okay, U, it's hyper, and you take any point in the graph, the hypergraph will lie above the tangent plane by convexity, okay? And this, we will use this to ensure that so we have our graph. We know that it will be between two levels, H2 and H2 alpha. Okay, so it is somewhere here. Okay, so if the graph, the idea would be that if the at any point the tangent, the hypergraph of our function lies above the tangent plane, and the idea would be is that if the tangent plane is very close to the cone, let me change the. If the tangent plane is very close to the cone, it will intersect this level, okay? And this means that since the graph is always above its tangent plane, this means that the graph will be above this level, okay? And this will contradict the fact that it is bounded by the level HR. So this is basically the idea. So it is really convexity at each step, and yeah, and this comes from the curvature of the metric. Okay. So so here I just draw an example where, so if the tangent plane is very close from one, the graph of the function must intersect the level H2R. Okay, and this will enter the proof of the rigidity part. Okay, so as I said, the problem is still has a solution, but we need to drop the condition about the curvature. Okay, so let me remind you the question. We have a pseudo-Riemannian manifold, and we have a closed orientable Riemannian surface, and we want to find a smooth embedding, which is conformal for this metric. Okay, so we will prove that once we have a spacelike embedding, then that's it. We can find a conformal embedding. So this is the only condition. So if we start with the spacelike, if we have a spacelike embedding, and here I drop. I am not talking about quotients of the cone. Any pseudo-Riemannian manifold, this will be the case here. So take any pseudo-Riemannian manifold and take a spacelike embedding such that there exists a spacelike embedding of sigma, which is closed orientable surface. And then for any Riemannian metric, you can find smooth, necessarily spacelike embedding of which is conformal for the metric G, and which is C0 close to the first embedding. Okay, and yeah, so C0 close here we have a pseudo-Riemannian metric. C0 close here, I mean, put any Riemannian metric on M, and we can find a conformal embedding C0 close for this Riemannian metric. It doesn't matter. Okay, so what is the idea of this? So I will start with this problem. If you take a curve in R2, okay, and some constant R, can you always find the curve? So you have some curve F0, okay, and you want to find a curve F1 such that it has speed R and it is C0 close to F0. So the first remark is that if the speed of f0, okay, if the speed of f0 is bigger than r, then this can never happen, because you see, you want to stay at speed r and you want to stay close to f0. This curve will be it has more speed, then uh, it will get away very quickly. But if you assume that the speed is if you assume that the speed of f0 is less than r, okay, at each point, then you can do this, because what you are going to do, you want to stay close to f0, but you have speed r, so you just spend more time around f0, and you do this kind of oscillations around f0. So you are close to f0, and you have big speed. Okay. So how are we going to do this? So maybe I will not talk about this exactly, but at least how can we find a curve such that its speed is c0 close to r, is as close as we want to r, and it is c0 close to f0. So for this, we will use convex integration. Okay. So convex integration is a method invented by Gromov to solve problems of this kind. Okay. So in the one-dimensional case, if we take our curve f0 in Rn in general, and let's suppose that we have a loop family. Okay. So for each point in 0, 1, for each point you have a loop. Okay. And that varies smoothly. When we fix the point x, we can take the average of this curve. And for some number n, we can define f1 like this. Okay. So what is the idea behind this is that, first of all, f1 will be c0 close to f0, because you see here, if x is an integer, then this thing will be 0, right? So this integral is one periodic, so it is bounded. Okay, and it is multiplied by 1 over n. So if you take n big enough, f1 will be as close to f0 as you want. And the second thing, if you assume that the average at each point of gamma is equal to the speed of f0, okay, then the speed of f1 will be almost equal to gamma at some point. So what is the idea? The idea is that you deform f0, you deform f0 in such a way that you have the speed, you have control speed. So if the norm of gamma is r everywhere for any point, this means that the speed of f1 is almost r everywhere. Okay, so it has speed close to r as we want. And this is and that's it. So you need only to find a curve of norm r, and that verify this average condition. Okay. So in the Riemannian setting, this will be possible if we assume the natural condition that we want. We said that we need the speed of f0 to be less than r. Okay. So let's take, if we are in this case, take the sphere of radius r. Okay, it will contain the f0, the speed of f0 will be inside. And since it is inside, so it is inside the convex hull of the sphere. Okay, and if you are in this case, if the point is inside the convex hull, you can always find a curve that lives on the sphere and of average equal to this point. So the condition that we wanted before is a very natural condition in convex integration, which is translated into a convexity condition. Okay, so here you take the curve, you start from this point, you start from this point, you go here, and then you come back. Okay, so this is your loop family, and you can verify that. Okay, I didn't give a formula, but this curve will, its average will be exactly the speed of f0. Okay, so if we just have this to satisfy, we can do this in the pseudo-Riemannian case. Okay, but we need to reverse the condition. We want this. We need for the speed of f0, we need it to be bigger than r, because when you take the ball of radius r in the pseudo-Riemannian setting, its convex hull will be in the other way. So the for f prime for f0 prime to be inside the convex hull of the ball of radius r, it needs to be bigger. Its norm needs to be bigger than r. Okay, and then you can find a curve that such that its average is equal to f0 prime. Okay. So what does this have to do with our problem? Of course, we can generalize this in higher dimension. Uh, so uh, uh, so we have a formula like the formula for one dimension. This is not the convex integration formula of Gromov. This is another formula called the corrugation process. It was defined by Thayer, and this formula is more easier to handle. This is why I use it rather than the convex integration formula. But the idea is the same. So let's start with this with some f0 with continuous map. Okay, on a cube, and we have for each point we have a loop. So we have a loop family, and since we are in higher dimension, we need to choose a direction. Okay, so we need to choose a direction where we add the waves or we add the oscillations. Okay. So if we choose the g direction, so here we integrate here just in the direction xg, and it will verify the same properties as before. So the map f1, what will happen? It will still be c0 close to f0. Of course, always with the condition on the average that it is equal to the directional derivative in in direction g of f0. Okay, we always need this condition. This is so f1 will be c0 close to f0. The derivative in the directions different than g will not change so much. They will still be close to the derivative of f0, and the derivative in the direction g, it will be almost equal to gamma. Okay, so the idea would be using this, we want to find epsilon isometric embedding, almost isometric embedding. Okay, so let's come back to our problem. Let's take a space-like embedding. Okay, and now if we take a metric which is short, uh, uh, short means just that the induced metric. So we said that this is a Riemannian metric. If we take this difference, this will still be definite positive. Okay, positive definite metric. So this is the usual condition. As we said before, this is just to ensure that the directional derivative of f0 will lie inside the convex hull of the ball. Okay, so just it's where it is a cheap condition here because we care about metrics up to conformal factor. So we are on a compact surface, so we can any metric we can rescale it to be short with respect to this metric, the induced metric. Okay, and now we will use the corrugation process to find an epsilon isometric embedding. So what we mean by an epsilon isometric embedding? It is an embedding such that the induced metric is C0 close to the metric that you want. And this is, remember, this is what we do, what we did for curves, right? We found an embedding with speed almost equal to r. Okay. So we can do this for metrics also. We need to do this in each direction, and so in each direction you need to do this, and you will get this always for any metric. You will get this. Okay. And just a remark here, you see that this idea of corrugation, you will do some things like this, and this clearly creates points of curvature, of different curvature, of positive curvature or negative curvature. Okay. Okay. So this implies that if you fix a conformal, if you fix a metric, you can find an embedding which is almost conformal for this metric, right? And using the equality that we used, this means that the set of metrics that admits a conformal embedding are dense, right? Because we can get close to as close as we want to any metric. Okay, so this means that we can get conformally close. So now what we need to seal the deal is topological argument. So we need the Brouwer's fixed point theorem to complete the proof. Okay, so what does this have to do with everything? So let me explain first of all what is the Brouwer, this variation of Brouwer's fixed point theorem. So if you take a closed ball centered at some point P0 and of radius r in Rn, and you take a continuous map from this closed ball to Rn, okay, and you just impose the condition that the image of any point, the distance between any point and its image is less than the radius r. Then the condition will the conclusion will be that the center will be in the image, okay. And this is a direct application of Brouwer's fixed point theorem. Okay, maybe I will not even go into this. So how are we going to use this to prove our theorem? Okay, so what is our problem? We have a closed orientable surface of genus D. This works even in the genus 1 case. Okay, we have pseudo-Riemannian manifold. And we have a spacelike embedding of sigma inside M. And we have a conformal class of metrics on sigma. And what's our goal is to find a conformal embedding of the metric G in MH. Okay. So what are we going to do? So first of all, we will take in the Teichmüller space, which is an Euclidean space, it is diffeomorphic to Euclidean space. We will take a closed ball centered at the conformal class that we want to realize. Okay. This closed ball, we will find a section of metrics in the Teichmüller space. So we can see it as set of metrics that represent this ball. And for each metric in this ball, we can find space-like embedding, okay, which is epsilon close. Okay, so this means that so we have a map. So we started with 0 in the Teichmüller space. We can find a section inside the space of metrics. Okay, so I will. So we have a set of metrics. I will call it 0 also, or 0 tilde. Okay. Now we have a set of metrics, and the corrugation process, we can do it with a parameter. Okay, everything works the same if we add a parameter. So what we are going to do is that for each metric in B rho tilde, we are going to find a space-like embedding, which is epsilon close for this metric. Okay, and when we take the projection into the Teichmüller space, so we have an induced metric by FQ for each Q in the ball. So this will give us a map from the closed ball into the Teichmüller space. And of course, everything will be continuous. If we do everything in the right way, everything will be continuous. We choose this section to be continuous. We do the corrugation process with continuous loop family that depends continuously on this parameter family. So everything will be continuous. So we will have a continuous map from the closed ball into the Teichmüller space, and which is just an Euclidean space. Now we apply, and of course, these we took them to be epsilon isometric, so we can take them to be the distance between any point and its image will be less than the radius. Okay, we can do this. So we have a continuous map that satisfies the hypothesis of our proposition, and this means that the center is in the image. Okay, this is what our the fixed point theorem tells us. And what does it mean to be in the image? It means that it is realized because all the conformal classes that are in the image of G are realized by some space-like embedding. So the conformal class of G is realized by some embedding in this family. So there exists some Q1 in the closed ball such that F the conformal class, if you take the induced metric by FQ1, its conformal class will be the same as G. And this means exactly that we are that FQ1 is conformal is a conformal embedding of the metric G. And we can also assure that all the embeddings are C0 close to the space-like embedding that we started with. And I think that's it for. Yeah.